This video describes 5 procedures in Statgraphics Centurion version 20 for detecting outliers in multivariate data. When analyzing multivariate data, it can be very important to detect unusual observations. Unusual observations are typically called either outliers or anomalies. There are a number of reasons why detecting outliers is important. First off, many data sets contain errors, and unless those errors are corrected, they will distort the results of any analysis or model fitting performed on that data. Secondly, highlighting unusual observations can help analysts know where to concentrate their efforts. For example, credit card companies can use these procedures to detect possibly fraudulent transactions. Version 20 contains a number of procedures designed to identify outliers. One of those procedures is the T-squared chart, often used for quality control. These charts flag points that are far from the centroid of the observations, assuming that the data follow a multivariate normal distribution. Another procedure is DBSCAN. DBSCAN is a cluster analysis procedure that flags as outliers points not belonging to any cluster. A third procedure for identifying outliers is isolation forest. This procedure creates a forest of decision trees and measures the average number of splits required to isolate each observation. Outliers typically require a small number of splits. Another procedure for identifying outliers is called local outlier factor. This identifies anomalies using a k nearest neighbors algorithm to estimate local densities. Outliers occur in regions of low density. The final procedure is one-class support vector machine. This procedure determines a boundary dividing outliers from other observations by first projecting the data into a higher dimensional space. As an example, we're going to take a look at some data collected in 2008 by the World Bank. Here you see a scatter plot of the life expectancy versus the infant mortality rate of 188 countries around the world. Our goal will be to identify unusual observations. We'll stick to 2 variables because it's easier to visualize, although the general principles extend to many more than 2. The first procedure we're going to look at is the T-squared chart. T-squared calculates the squared Mahalanobis distance of each observation from the centroid of the data. Subtracting the means and multiplying by the inverse of the covariance matrix both standardizes the data and accounts for any correlation. Assuming the data come from a multivariate normal distribution, the value of t-squared, which is exceeded with the specified probability alpha, can be determined. Here you see a t-squared chart for the 188 countries. The horizontal line has been drawn at 9.02, which is the value of t-squared, which would be exceeded 1% of the time. There are a total of 6 countries above the line. Those are the potential outliers or anomalies. Since we are working with only two variables, the critical value of t squared that contains 99% of the multivariate normal distribution can be shown by drawing an ellipse. Our 6 potential outliers fall outside the ellipse. Notice that Sierra Leone has an unusually large infant mortality rate. The other 5 countries do not have a large infant mortality rate, but they do have low life expectancies given their infant mortality. Another popular method for identifying multivariate outliers is called DBSCAN. DBSCAN stands for Density-Based Spatial Clustering of Applications with Noise. It's used to divide observations into clusters, which are groups with similar characteristics. DBSCAN uses a nearest neighbor algorithm to determine which observations belong to which clusters. The user specifies 2 parameters. The first parameter is the maximum distance epsilon between 2 points for those points to be considered neighbors. The second is the minimum number of joint neighbors required to create the core of a cluster. Each observation in the dataset is classified as one of 3 types. First, there are core points. Those are points within the core of a cluster. All the core points are neighbors of each other. The second type of point is a border point. A border point has a neighbor that's a core point of some cluster. It's assumed, therefore, to be a member of that cluster. And finally, there are outliers. Outliers are points that don't have any core points as neighbors. Here you see the result of DBSCAN run with the default values for the parameters. It identifies a single cluster containing all but 4 of the countries. I've added a convex hull surrounding the cluster, connecting the border points. DBSCAN has 2 major advantages over other clustering procedures when it comes to identifying outliers. First off, you don't have to tell it how many clusters are present in your data. It will figure that out as part of the algorithm. Secondly, it can identify clusters with complex shapes. For example, here's the classic example of 2 moon-shaped clusters. A third procedure in Statgraphics version 20 for identifying multivariate outliers is called isolation forest. Isolation forest creates a forest of decision trees in order to determine which observations are outliers. Isolation forest assigns an anomaly score to each observation based on the average number of splits required to isolate that particular observation across all of the trees in the forest. Observations with the smallest average number of splits are most easily isolated from the others, and therefore most likely to be outliers. The most important parameter that the user must specify when creating an isolation forest is the level of contamination. That's the expected percentage of the outliers in the data. This is a parameter that often needs to be tuned to get the best results. This is a plot of the anomaly scores assigned to the 188 countries in our data, assuming a contamination level of 5%. 9 of the countries are above the outlier threshold, which is 0.58. Any observation above that threshold is classified as an outlier. Any observation below the threshold is an inlier. That threshold can also be used to classify additional observations not in the current dataset. When there are only two variables, it's useful to display the anomaly scores using a heat map. In this graph, the bluer the area, the more likely the data point is to be an inlier. You can also see a border drawn separating the inliers from the outliers. A fourth method for identifying outliers in Statgraphics version 20 is called local outlier factor. Local outlier factor estimates a local reachable density for each observation using a nearest neighbors approach. Observations in areas of substantially lower density, that means fewer close neighbors, are classified as potential outliers. The user specifies two parameters. First, the contamination, that's the expected percentage of outliers in the data. And second, the number of neighbors used to estimate the local density. The local outlier factor procedure also generates anomaly scores. Here you see a plot for the 188 countries, assuming a contamination level of 5% and using the 20 nearest neighbors to estimate the local density. There are 9 observations identified as being outliers. You might note that these 9 are mostly different than those identified by the other procedures. The heat map produced by this procedure is considerably different than the last one we looked at. Notice that the areas of high density, that's the blue areas, are much narrower in the upper left corner than toward the bottom right. This means that observations in that upper left quadrant do not have to be as far off the diagonal to be classified as outliers as some of the others in different areas. The fifth procedure, available in Statgraphics version 20 for identifying multivariate outliers, is the One-Class SVM, support vector machine. This procedure transforms the data to a higher dimensional space and then searches for a hypersphere or a hyperplane that encompasses the majority of the observations. One-Class SVM attempts to maximize the boundary area between the majority of the observations and the others. Observations outside the bounding hypersphere are classified as outliers. There is a single parameter that the user needs to specify to tune the One-Class SVM. That's the contamination, the expected percentage of outliers in the data. Here you see the anomaly scores produced by the One-Class SVM when the contamination is set to 5%. Most of the outliers have been detected earlier, although there are a couple new ones. The anomaly contour plot for the one-class SVM is similar to what we've seen before, although perhaps a little more dramatic. I've shown you 5 important procedures in Statgraphics version 20 that can be used for detecting multivariate outliers. These procedures can be used in many different areas. They may be used for cybersecurity threat detection, fraud detection, early disease detection, patient monitoring, fault detection, predictive maintenance, demand forecasting, financial planning, energy monitoring, environmental conservation. And that's just a small fraction of where they can be used.